Record to this computer. There we go. Okay, as I was saying, so we're going to look at this thing today called Big O notation, and this is going to be the tool that we use for asymptotic analysis, as well as how to actually analyze the runtime of our algorithms a little more rigorously. Last time we threw around a lot of words and phrases like roughly, n time, and constant time. Today we're going to take a little closer look at what exactly that means by investigating some other kinds of algorithmic problems. Before we dive into that, though, any questions about anything? Any admin stuff that we want to get out of the way, or everyone have a good weekend? Yeah. Okay, cool. Yeah, well, let's get into it today. A significant portion of today's lecture is going to be on the blackboard, as well as some accompanying code. But I'll be recording this and capturing it with my crappy laptop camera that hopefully will show up when I upload the YouTube recording. We'll see how that looks. But okay, so I want to take you guys back to the start of this course. It seems very long ago now. It was what, like a month, something like that. We've seen so much. We've grown so much together since then, all of us on this journey into programming. And there was a problem that we looked at closer to the beginning of the course, which was this very simple problem of I give you a list and I want you to find the max of that list, right? Bless you. It could be like a list of, let's say, integers, just to simplify things a little bit. So I give you a bunch of numbers, you go through the list and you try and find what the biggest number is, right? Simple enough. Hopefully we all remember roughly how we kind of approach this. Um, I guess we can like do a quick little. So we kind of had this algorithm that sort of looked like this, right? I have some function find max, and you give me a list. And then all I have to do is I step through the list, right? And I know there's like an actual explicit function that Python lists provide that allow us to do this, but for the purposes of our algorithmic analysis today, we're going to spell it out a little bit here. So for I in some list, and then we had this like temporary max that we were storing. If I is less than or greater than the temporary max, then we set the temporary max equal to I, and then we would just return I at the end of this, right? And then we actually need to say, okay, in the beginning, temporary max is just going to be whatever the first thing in some list is, just as like a placeholder value. So this is like this very, very simple little snippet of code to find what the max in our list was, okay? But now I actually want to talk about what the precise runtime of this algorithm is. So we're going to call n the length of some list. And in general, when we talk about algorithmic analysis, n usually refers to the size of our input problem, right? And it depends exactly on what kind of problem you're working with here. But for the purposes of like this, and like we're talking about a list, n is going to be the number of elements in our list, right? And so, okay. So what is the runtime? The question that we're going to be answering right now is what is the runtime of this algorithm as a function of n, the size of my input? Okay. So we can actually do this ourselves, right? If we step through this code, we can attribute a cost to each one of the steps in our code, right? We can say, okay, this assignment operation will say takes one step, right? And then, I don't know, initializing this list, maybe under the hood, we know that this is going to run like roughly n times, depending on where exactly the max in my list is. So we'll say that this loop runs. And then each of these comparison operations takes one step, right? And this assignment operation also will assign a value of one step to this. And the return here is also one step, okay? And then how many times does this loop run? Well, this loop runs up to n times, right? And so the particular kind of analysis that we're going to be looking at today, there's a couple different ones, but we're going to be looking at what's called worst case analysis. And this means what is the longest your algorithm could take on the worst possible input? In other words, for this particular problem, right? What can someone imagine what a worst case input in terms of runtime for our find max function would be? Well, it's all of them because I need to like step through the entire list no matter what, right? In order to know that I found the max element, I need to go through the whole list. Yeah. So, okay, then we can say that by summing all of these things together, we have one step here. This goes through n times and it does each of, these operations. Potentially in the worst case, right? It could reassign this max. Like if we have a list, actually, this is what the worst case for this algorithm would look like. If we have a list that's sorted in ascending order, right? Then every single element that I see would be the new max. And so I would need to run this reassignment operation on every single iteration of the loop. So in the worst case, both of these steps fire on each internal iteration here, right? Inside each of these iterations. And then there's one final step to actually return the thing. So in total, the total runtime is 1 plus 2n plus 1, right? Which is another way of putting this is 2 times n plus 1 steps. And we could say this is the runtime of this algorithm. Yeah, there's a question over here. Yeah, I should. This I shouldn't put up to n times. This always runs n times. Yeah, that's correct. Yeah, yeah. Yeah, this is why. So this you're asking really good questions right now. This is why we specified that we're looking at the worst case analysis of our algorithm, right? Because it's true that for some given list, this comparison operator won't always be true, right? But in the worst case input where it's sorted in ascending order, then this comparison is going to evaluate to true every single time, and we're going to have to reassign every single time. So in the worst case, the technical name for this would be the worst case time complexity of this algorithm would be this, right? Okay. So let's take a look at another example of an algorithm, okay? Maybe instead of finding the max, what we want to do is we want to find the absolute value, right? The element with the absolute maximum value in my list. In particular, let's say the index. So find index of absolute max, okay? And actually, in the interest of being consistent with find max, let's just say find absolute max. So this will return the element in the list with the absolute maximum value, right? So again, let's see how to do this now. So again, you're going to give me some list. And again, I'll store like the temporary absolute max value in here. We'll just set it equal to the first thing, sum list sub 0. And then same as before, we're just going to step through this for I in sum list. We're going to do if I, well, now we have to do a little extra check here, right? Because we're looking at the absolute value. So we're going to say, one way of doing this is we could say if I is less than 0, right? Then we're going to reassign I to be I times equals -1, okay? And now we're going to look at, we can actually do the same comparison that we were doing before. Now we can just say, okay, now if I is greater than the temporary max, absolute max, then we update the temporary absolute max here to be I. Yeah? And then same thing as before, we're just going to return I, or return temporary absolute max. Okay, so question for you guys. What is the worst case time complexity of this algorithm now? Worst case time complexity. Does anyone want to take a crack at what this is? Yeah. Yeah, exactly. If they're all negative values and they're in ascending order, that's like the absolute worst case, right? So for that really problematic input, yeah, question. Okay, yeah, no, that's a great question. So to illustrate this, so let's go back to this find max example. And here, I'll switch on my, whoop, now you can all see me, even the people at home. Where's my chalk? Okay, so we like let's imagine that this was the list we wanted to sort, right? Maybe it looked like seven, or not sort, sorry, but find the max of three, two, one. Okay. So the way that this find max works is it would start by setting I to this, right? And it would assign this to be the temporary max. And then it would compare it to each of these things. So it has to do these comparisons no matter what, right? But because this is already the biggest element, we never actually run whoop, this thing, right? This reassignment operation never runs. And so in some sense, this is a best case scenario because we save on all those potential reassignments. So this example here would be an example of a best case input for this problem, right? But then we can imagine the exact opposite scenario where our list actually looked like this. 4 and 7, right? Instead. And now, okay, we're doing the n comparisons that we were doing before, but now because every single time we're looking at the least element among all the elements that we haven't actually looked at yet, then every single time I need to do this reassignment operation, right? And so this is why this is like a worst case input. So if we were to do the best case time complexity of this algorithm, we just wouldn't count this, right? And we would say, okay, in the best case, it's just 1 plus n plus 1, right? So equals n plus 2. Are we starting to see the difference between best case and worst case here? Did that sort of answer your question?
Yeah. Tell the concept why there's a best case because then one of the functions still go through all of them to make sure that the first one is the biggest.
Yeah. So in both cases, we're going through all of them, right? But in this case, we also have to run this line here on line 6 on every single iteration. And in the best case, we never have to run this line. So we save on all these reassignments. But in both cases, we're still iterating through the entire loop, right? Yeah, question. Oh, so I have 2n for the worst case because this loop runs n times. And for each iteration of that loop, we do two things. So it's n times 2.
Oh, and one step in the loop.
Yeah, exactly. In the best case, it's n times 1. And in the worst case, it's n times 2. That's exactly right. Okay, good questions. Good questions. Okay, so if we're clear on the difference between best case and worst case now, let's go back to doing the worst case analysis of this find absolute max function. So same as before, right? Like we always know this is going to be, I'll do it out here now. So this is always going to run n times, right? This loop runs n times. And in the worst case, right, this comparison operation takes one step. This reassignment operation takes one step here. And then I have another comparison operation that takes one step, another reassignment operation that takes one step. And then this takes one step, this return, and this assignment at the beginning also takes one step. So what is the total worst case time complexity of this algorithm? Yeah, exactly. It's 4n plus 2. Was there a question over there, Mathilde? You had a question?
People compare tolerance, but also compare the ones in orange.
Yeah, yeah. So the comparison operators always run, right? So what's the best case time complexity here? In the best case, we always do these comparison operators, but they always evaluate to false. So we never do these conditions. And then it would be 2n plus 2, right? Because we're doing two comparisons per iteration and we're iterating n times. So in the best case here, so we could say, okay, the best case time complexity is 2n plus 2. Yeah? And in general, when we do algorithmic analysis, we don't talk about the best, like, we're not really optimists in the computer science world. We don't really talk about best case time complexity that much because it's very, very rare that you actually encounter the best case scenario of an input in the wild, right? Like, we like guarantees on how long our algorithm is going to run in the worst case possible, right? To be sure. And that's why very often we look at worst case time complexity. Another kind of analysis that you might see is average case time complexity. And this is what is the expected runtime of my algorithm on an input selected uniformly at random, right? Or maybe from some distribution over the inputs that I'll see. But the analysis for those, for like average case analysis is a little more involved. So we won't look at it too closely in this course, but it's just something that I want you guys to be aware of. Okay, cool. So now, oh yeah. So I'm, this is you'll notice that I've been like calling certain things one step. And a legitimate question you might have is like, okay, but what qualifies as a step in my algorithmic analysis? Is it always just like some line of code equals one step? Well, maybe not, right? Because if I had some code that looked like, I don't know, some function here, right? And it maybe does something, it accepts a key. And then I do, maybe I have like a binary tree from the example of last class, right? So I have some binary tree node, right? Root. And this is equal to a binary tree node here thing. And then I do something where like I add a bunch of stuff to root. And then I do root dot insert some new key, right? So would this also just be one step here in my accounting of the algorithmic analysis for this? Well, it kind of depends, right? If we have like, I don't know, maybe we could just call this like insert stuff into tree, right? Maybe this is what my function does. And then you give me like some list of elements. And so some list has n elements. So should this just be one step here? Right? If I want to like insert some key maybe that I look at a little bit earlier in the code. Not exactly, right? Because if you remember from what we saw last time, right? Like each of these insert steps actually consisted of a bunch of comparison operations as we were walking down our binary tree to figure out where to put it in our list, right? So in the worst case, for a non-balancing tree like the ones we looked at last time, in our accounting of what the runtime of this algorithm is, we would have to say this takes n steps, right? Because in the worst case, we would have to see that, like we would have to compare against everything we've inserted into the tree so far, right? So I just want to illustrate that it is not the case that one line of code equals one time step, right? You can have one line of code, but under the hood, it's actually doing many, many atomic operations that are worth one time step. And so because of that, I just want to like, as an overview, we'll just say the operations that take one time step are things like, okay, comparisons, reassignments, basic arithmetic operations like plus, times, multiply, divide, like each of these things takes one time step. Um, and I can't think of anything else off the top of my head. I'll call them as I see them though. But yeah, like each of these things you can safely say, okay, this takes exactly one time step in my code. But you have to be mindful that sometimes when you call a certain line, right, or some function, and you're trying to figure out what the runtime of this is, just because it's one line of code doesn't necessarily mean it's one time step. Okay, that's all that this was to illustrate here. Any questions about this? All right. In that case, I want to move on to introducing big O notation. Uh, so it turns out that, like in this example here, right, where we were looking at find max and find absolute max, this is kind of tedious, right? Like if I have to go in and count every single operation, like it turns out this is more work than we need to do a lot of the time. Um, so it turns out that in computer science and in these like in algorithmic analysis in general, we don't care too much about the specific constants or coefficients that appear in our expression. The thing that really dominates how long this algorithm is going to take to run when we start looking at gigantic inputs are the actual functions, like the non-constant functions of n here, right? Like this linear uh, n in the size of the input. So to account for this, computer scientists introduced this thing called big O notation. And what that looks like is so that we're going to go, it's like a bit of a fancy mathematical definition here that we're going to see. Um, so given two functions, let's say f and g are functions, then we say that this is just a definition. F is in big O of g of n if there exists some, and this is just a mathematical symbol that maybe some of you have seen before that just means it exists. There exists some number m such that, can we still see here? Such that for all natural numbers n, okay, f of n is less than n times g of n. There we go. For the people, that's a G, I swear. Okay, and I've like just regurgitated a mathematical definition at you, but let's actually see intuitively what this means. Um, so for the concrete example of this find max that we were looking at before, right? I I want to find some because I don't really care. All I care about is the presence of this n here. Um, I want to find some constant number, some natural number, right? So that this worst case time complexity, right? Because in this definition here, um, the worst case time complexity is f, right? That's kind of the role this is occupying. And I want to find some nice, cleaner function that doesn't have all these messy constants in it and stuff, that can kind of bound what the runtime f of my algorithm is. Okay? And so you'll note that because the runtime here is 2n plus 1, then in fact, I can just say, well, I know that for all, like, I can put it in a comment here. For all n, I know that 2n plus 1 is bounded above by 3n, right? This is just a simple mathematical fact. And so therefore I can say the worst case asymptotic time complexity of this algorithm is big O of n, right? Because I have this constant 3 that I can throw in front of n that always bounds the runtime f of this algorithm, I can just say, I actually don't care about any of these constants. This just runs in, we would say, linear time, big O of n, right? This is in some sense the term that we care about that dominates the runtime, defines in some sense the runtime of this algorithm, okay? Um, any questions about this? This is a bit of a tricky, like unintuitive thing at first to wrap your head around, but you'll see that when you actually start analyzing algorithms yourself, it simplifies things so much. Um, because now I can ask you, okay, what is the asymptotic runtime of, or what's the asymptotic worst case time complexity of this find absolute max function here? Does anyone want to take a guess? So this is what it looks like here, right? This is the actual specific or finer grained time complexity. So because I can just find like, I know that 5n is always less than this, right? Therefore, I can say the asymptotic worst case complexity is also O of n for this. So asymptotically, find absolute max and find max take the same time, right? This will become a little clear when we start looking. I think this will become clear when we start looking at algorithms that don't have linear runtime, linear asymptotic runtime like this. Like this. Yeah, question. Oh yeah, so O is just big O of this function Gn is the class of all functions that satisfy this property, right? That in some sense are asymptotically at most what this function g of n is. So g of n here in these examples, so this is just n, right? And f is the runtime of my algorithm. But people use this notation. The reason why I stated it more generally like this is because people use it for other things too. But for the specific purposes of runtime analysis, we can always think of f as referring to the runtime of our algorithm, and g of n is like some asymptotic class of complexity that we want to use to classify these f's, right? Okay. But yeah, yeah, question?
For example, for E someone's function.
Is is the sorry, could you repeat the question?
As
So the asymptotic, the word asymptotic just means we want to look at the behavior of this thing as n gets very, very large, right? And we don't care so much about the exact additive and multiplicative constants in the expression. We're really just, it's kind of like, I'm going to erase this definition here for a second. So we can compare two functions, right? So the functions, I'll just use this solid line to indicate the functions in O of n, and this dashed line to indicate the functions in O of n squared. Okay? Well, but basically, right, like no matter the only things that kind of change, like I'm interested in the behavior as n approaches infinity. of my function, my like time function t of n that gives me the runtime of my algorithm, right? So no matter what linear function you give me, right? It could be n like this. It could be maybe like 1/2 of n, and that looks like this. It could even be like 2n plus 5, which maybe looks something more like this, right? Like these are all roughly behaving the same way when you look at them on the scale of n approaching infinity, right? On the other hand, if we look at a function in O of n squared, right, like n squared, then this looks more like this, right? Or something like that. And so no matter how, in some sense, what asymptotic notation allows us to differentiate is the fact that no matter how big, right? If you give me some linear function L of n that looks like, I don't know, mx plus b, no matter how big m is, okay? I can even do this here. No matter how big m is, no matter how big b is, right? Like you could give me the most crazy looking, like close to vertical line that you want to give me. At some point, this n squared is always going to be bigger than it, right? Just because we're square, like taking the square at infinity is a much faster growth rate than any linear function that you give me, right? So this is why we talk about asymptotic complexity. It's because I'm interested in the behavior of these time functions as we look at gigantic inputs, right? And at that scale, these exact constants don't matter so much. Yeah, question.
But does that just mean like, because the coefficient, like the second one that we did with like the absolute, even though like that one was bigger than the first one that we did, which was just like n2, n+1,
Uh-huh.
they would like at really like large scale behave the same, or like they would have the same
They're,
like n.
yeah, they're both part
Like
of
they're
this.
both linear. It doesn't really matter.
Yeah, exactly. Right. And that's kind of what asymptotic notation is really getting at. Other questions about this? These are good questions. Okay, so with that, I want to introduce, rather than speaking hypothetically about O of n squared, I want to actually introduce a concrete algorithm that has a runtime in O of n squared. And then this will help us differentiate between these two things. Okay, so let's have another function now. We could just do like to indicate that we're moving on to other things, bigger and better things. So let's have a function now where instead of finding the max of a single element, I want to find the maximum partial sum in a list. Okay, what does that mean? So to kind of illustrate my point here of what I'm talking about, so you give me some, we're working with lists of elements again, right? So maybe it looks like 3, 2, -4, 2, -7. Okay. And I want to find the largest partial sum from the start of the list to somewhere in the middle of the list. Okay. So we can actually explicitly compute this. We can say, okay, the partial sum up to the first thing is 3, right? The partial sum up to the second element becomes 5. We add 3 to 2. Yeah. And then, okay, we add -4 now. So this partial sum becomes 1. We add 2 here, the partial sum becomes 3 again. And then we subtract 7, so the partial sum drops down to -4. So what is the position of the largest partial sum in this list? Just put the biggest number over here. It's just 5, right? It happens. So this, we could call this function like, I don't know, find max partial sum, and it would return 1. right? Because one, at position one, that's where we observe the largest partial sum in this entire list. Okay? Cool. So let's actually program this, okay, to take a closer look at it a little more explicitly. So we'll call this find, and instead of getting the index so that we're consistent with the find max that we've been looking at so far, let's just find the largest partial sum and return that, okay? So now we're going to do find max partial sum. And again, you'll give me some list of integers. Okay. Does anyone want to suggest maybe how, like at a high level, we should do this? Any ideas or suggestions? Yeah.
Do you want to define this list that will append our numbers to like our new numbers that we calculate with the partial sum?
Yeah. So like on each iteration, we kind of keep this running track of the partial sum that we've observed so far, and we populate this new list with it, right? Yeah, that's good. That's one approach we could do, but that's actually a lot smarter than what I was hoping you were going to say. I really wanted like the dumbest possible thing that we could do. We are going to implement the solution that you're talking about in a second, and this is going to be a nice way of differentiating between quadratic and linear runtime. But for now, we're going to do something even dumber than that, which is let's just step through this list and recompute the partial sum up to that point every single time. Okay, just literally the dumbest first thing that you might think of. So we can do this by again, we'll keep track of a temporary variable that I'll just call temp here. And in the beginning, this will be like the first thing in the list again, sub 0. And now, okay, now we're going to have a loop. We're going to say for I in some list. And here's the thing, we're going to want to step through our loop, right? We're going to keep something called keep track of a sum here. And in the beginning, it's just going to be 0. Okay, let's not call it sum because that's the name of built-in. Call it temporary sum is equal to 0. And then we'll just reiterate through our loop up until that point. And we'll say, okay, well, for j in some list up until I, right? This is just, we're using this slice notation to get that relevant part of the list here. Sum or temp sum plus equals j. And then we'll compare, we'll call this temp max sum. 65, go. Now we'll say, okay, if the temporary sum is greater than the temporary max sum, then we update. We say, okay, the temporary max sum is now equal to the temporary sum. Yeah. And then at the end of this, we just return what the temporary max sum is. So this looks sort of what we were doing like before, right? With the, what's it called? When we were just finding the max. But now I have this inner nested loop, right? That I'm running. And so, okay, let's do the worst case time complexity analysis of this, right? All right, so this assignment operation, this just takes one step, okay? Now this outer loop runs n times, yeah? And so for each of these, I'm initializing a new variable, so this takes one step. And then, aha, how many times does this run, this inner loop now? Does anyone see it? Like for the ith iteration of this outer loop, how many times does this inner loop run? Yeah, exactly. It runs I times. Okay. And then each of these takes one, right? This addition operation takes one step. This comparison takes one step. And this reassignment takes one step in the worst case. Okay. And then we return here. This also only takes one step. Okay, so what is the worst case time complexity of this algorithm? How will we do this? Does anyone have any, want to throw out a guess on how we might approach the analysis of this algorithm here? We want to write some mathematical expression, T, right? What we're looking for is like some T of n, where n is the number of things in my list. Ooh, I'm not actually. Where n is the number of things in my list, and T is just the name of like the worst case time complexity of this algorithm. So what might this look like? So let's step through it a little bit and see. So in the worst case, right? Oh yeah, question?
I don't know. Sometimes
Oh yeah, so for the we'll call the like returning is only taking one time step, right? Now you could do something where like you return the, I don't know, like you could return some operation on something here, right? And this then might take more than one time step. But if all you're doing is returning a constant that you already have, like temp max sum here, then this only takes one step. Okay. Yeah. Okay, so back to looking at the runtime of this find max partial sum function. Um, let's work with a concrete example here. Okay. I think that'll really drive the point home to find out what this Tn looks like. So in the example that we had before, so let's try and imagine what is the absolute worst case kind of input that I can run into when I'm working with this problem, right? It's the one in which I need to do this reassignment operation every single time, right? Which means on every single time step, the partial sum is the smallest it's going to be for the rest of the list, right? Or no, it would be the other way around. It would be the, yeah, I think that's correct. I think I said it the right way. So it would look like, I don't know, something like some ascending list, right? We could have like 2, 4, and then I'll start a little more over here. We'll have like 2, 4, 7, 10, 11. Maybe that's what our list looks like, right? So now as I'm stepping through this, I'm saying, okay, so in the beginning, I only loop up to this thing, the sum is 2. And then it's 6, right? So I have to do the reassignment, and because this 6 is bigger than the partial sum that I computed so far, okay? So at each step, we'll do what the partial sum is, and then we'll do the max partial sum that we've seen so far. So here, the biggest one that I've seen so far is 2. And then I recompute the partial sum up to this point. I get 6. So the biggest one that I've seen so far is 6. And then, okay, I add this to this. This is going to be 13. Again, this is bigger than this thing. So I have to reassign the partial sum here. This becomes 13, right? And so between the best case and the worst case, the number of times that these loops are running isn't changing. It's just that we have to do this reassignment every single time, right? So, okay, then let's just focus on what the worst case time complexity of this thing is. So at each time step here, right? Like, let's say I want to do this. I want to consider 10 now. So this, I know this is going to be 23, right? Just by looking at this. But what I actually have to do is, what's happening under the hood is this is, like at this point, the value of my outer loop is equal to 0, 1, 2, 3. Right? We're looking at the third element of the outer loop. But then this inner loop needs to run up to I times, right? So it's going to do 1, 2, 3, 4 iterations of the inner loop. And so we could just write as a temporary intermediate function here the runtime h of my algorithm on the ith iteration of my inner loop is equal to I, right? If I'm just letting this h function represent that. So then the total runtime of my algorithm, t of n, okay, let's take a look at the algorithm again here, is going to be 1 for that first temp max sum there, plus n times, well, this is the thing, right? We'll model this as a sum actually, but it's going to be the sum from I, and this is a different I here from what I've written there, from I equals 1 up to n of the actual partial sum, which takes I time steps, right? Read that, plus to j there for that, and then times 2n in the worst case, okay? Plus 2n for those two, plus 1. So I'm going to explain how I got this in a second. I just want to show it to everyone who's watching on the recording. So this is what my worst case time complexity of this algorithm would look like. It would be 1 plus the sum from I equals 1 up to n of I plus 2n plus 1. Now, how did I get this? So this thing here, this first one, this is the assignment that happens at the beginning, okay? And now this inner sum here, it's 1, 2, 3. Okay, well, technically it would be 3n. Right? And so now this portion here, this is what happens in the loop, right? This is the outer loop runtime here. Whoop. So this is the runtime of the outer loop, right? And this is the runtime of the inner loop. So you can see that this inner loop runs up to I times, where I is changing on each iteration of the outer loop. And that's why I've expressed it this way, okay? So it's going to be the total number of times that this inner loop fires is going to be n plus the sum of the first I things, right? As I is changing on each iteration. And then this 3n here, that 3n, right, that appears in the expression, this just captures everything else in the inner loop, right? This gets this, temp sum equals 0, this counts this, and it counts these two steps here, this comparison and this reassignment that happens, okay? And then we add one more to the end for the actual return operation at the end. So does everyone kind of follow what the worst case time complexity analysis of this algorithm is that we did here? It's okay if you don't. Please ask questions, and I can explain more. But just so that we're all we see where each of these terms is coming from. Yeah? Or like this captures the inner loop. This captures the other stuff in the outer loop, the return and the initial assignment. Okay. This is kind of this is a bit of a messy mathematical expression though, right? Like we have this I variable here that's a function of, it's like this summation thing. So let's see if we can clean this up a little bit. So I'll erase, I wish I had more board space. I guess I'll do it up here. Actually, what I'll do is I'll record this here. I'll say, okay, it's going to be equal to 1 plus the sum from I to n. That's just this little notation that I'm doing here of I plus 3n plus 1. So let's see if we can massage this a little bit. So I'm curious, has anyone, like this expression here, right? The sum of the first n numbers. Does anyone know another way of writing this? Maybe that you've seen in a math class or something? Yeah?
N plus 2, 6.
Something like that. Yeah, yeah. You're close. You're close. There's a way of writing this purely in terms of n. Okay? And it actually looks like this. N times n plus 1 over 2. But how do we... Oh, I'm just realizing now. In the recording, is it going to be like... Maybe that's not super helpful for everyone. Maybe there's a way that I can mirror that later. I'll have to see. But yeah, or you guys are maybe you're just really good at reading backwards. And okay, we'll fix that later. That's funny. I didn't think to consider that. Okay, so let's actually, how did I get this? So another way of writing this, let's call Sn the sum of the first n numbers. Okay, the first n natural numbers. So this looks like 1 plus 2 plus 3, da da da, so on, up to n, right? Sure, let's do it this way. So how can I write a mathematical expression that simplifies this? Well, let's add this back to itself. So if I say S of n is equal to, I'll just rewrite it now, n plus n minus 1 plus n minus 2. Like I'm just rewriting this sum, I've just flipped it. Okay, nothing magical. I'm not deceiving you in any way. Up to 1. So if I add these two things together now, what do I get? If I just add, like I take a big sum here, both of these. And what I get is 2 S of n is equal to n plus 1 plus n plus 1 plus n plus 1. Da, 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 da. How many times? How many times do I see this n plus 1 term? Sorry, maybe this is a little low. Right? How many times am I going to count this? And it's given here. Yeah, exactly. N times. Whoever said that, that's great. So this then, I'll rewrite this up here. So then we know from this that S of 2 times S of n is just equal to n times n plus 1. Or equivalently, S of n is equal to n times n plus 1 over 2. Okay, this is the derivation of that sum that we saw a second ago. Like the sum of the first n numbers is this expression here. Okay, so in particular, we can rewrite. We can rewrite this worst case time complexity that we had here a second ago. So this was T of n is equal to this thing. We can rewrite this to look like T of n is equal to 1 plus n times n plus 1 divided by 2, right? Plus 3n plus 1. Okay? So, all right, we've gotten rid of this. We now have a closed form expression for this, right? So does anyone want to try and guess what the asymptotic worst case time complexity of this algorithm is. In other words, what big O class does T of n belong to? This is the cool part about asymptotic time complexity is that you could just look at this entire expression here and see that there's n times n plus 1, right? Which means there's going to be some n squared in this expression. And that term dominates everything else as n approaches infinity. So you can just say T of n is in O of n squared, right? Okay, that's way better than working with this expression here, right? And in fact, the way that we actually write this the way that you'll see it written in practice is people don't say T of n is in O of n squared. They'll write confusingly, uh, T of n equals O of n squared. This is just a way of meaning this, that T of n is in O of n squared. Okay? And as you get better at this, like this is the reason why I went into such detail over showing you what this part, like this sum of the first n numbers evaluated to in a closed form, is because you'll see this often, you'll see it over and over and over again, like when you're doing your own analysis of your algorithms. And like oftentimes you can just look at a doubly nested loop like this that's stepping through the elements of your array. And like, I wouldn't like when I look at this, I don't even have to do this breakdown of the steps. I just see a doubly nested loop and I'm like, oh, it's O of n squared, you know? Like that's the neat thing about this asymptotic notation is you can kind of just recognize the larger pattern of the algorithmic structure, see that like the bulk of its runtime, where it really comes from, is from this doubly nested loop, and allow you to say this is O of n squared, right? Without needing to worry too much about what exactly is happening on each step. Yeah, question. Yeah, so what it tells us is how the algorithm, how fast the algorithm is when n gets big, right? Like if this O of n squared here, like the n squared is going to grow so much faster than any linear algorithm, like any linear runtime algorithm ever will, right? So what this tells us is that find max partial sum is a lot slower than find max, as we've written it right now. It is asymptotically slower than find max. And in fact, if we were to do a side-by-side comparison and like time the runtime of each of these algorithms as some list grew, you would very quickly see as n starts to grow that find max would crush find max partial sum, right? Like the comparison would be super obvious, right? And really the essence of that huge gap in runtime that you start to see comes from the fact that they belong to different asymptotic runtime classes. Like n squared is way, way bigger than n, right? So in general, when you're designing algorithms to work on lists like this, if you can think of a clever way to get it to run in linear time, you always want to do that over something that runs in quadratic time, right? This is in some sense, to answer your question, it's in some sense the difference between a smart and a dumb algorithm, right? Cool. Any other questions about this? Yeah. Yeah. So pretty much like every the ones that you commonly see in practice a lot when you're talking about the runtimes of algorithms is like we could do common asymptotic complexity classes, are things like you see O of n a lot, right? Linear time. You'll see O of n squared. Another one that you see a lot that we'll actually see next lecture is O of n log n. And where the log here is base 2. And actually, let me put these in order of increasing time complexity. So O of n log n is worse than O of n, but a lot better than O of n squared. It sits somewhere between these two classes, right? And then, when you get into things like matrix operations, You'll even start to see things like ov n cubed. This is another one that you'll see. And so yeah, it really like makes talking about algorithms nicely because rather than needing to worry about the exact breakdown of every time step, you can kind of bunch algorithms together into these nice classes where we can say, hey, for this problem, ov n's really good, ov n squared, not so much, right? There was another question in the back.
Is linear the smallest or is there like a root? Is this like the smallest one?
So it's the smallest one that we'll see in this class, but it's not the smallest one that's out there in the literature. Like there are people who work on sublinear algorithms. And you'd see those in like certain settings like streaming, I think, that we won't really touch on here. But yeah, there are people, you do see algorithms where it's like,
Iterating through lists. It's like it's n, but like what if it's not like a loop?
yeah. So how do we do this when we're looking at other types of data structures? Well, an example of this is a great example of this is the binary tree thing that we saw last time, right? Like if we go back to lecture, whoops, we'll do this, quit. Lecture 12, we open up binary tree search. So remember the binary tree example from last time. So this insert operation, the runtime complexity of this in the worst case is n, right? Because we kind of saw this example last time of like, okay, well, if I have this like 3, 4, 6, 7. Okay. Then maybe like 9. Then the way that my binary tree would be structured is I would say, okay, 3 is going to be at the root, and then 4 is bigger than 3, so its right child is going to be 4. 6 is bigger than 4, so its right child is going to be 6. And then 7, and then 9. So this is an example of, and that just for people who are wanting. So this is an example of a worst case input for binary tree insertion, because every time I need to go through everything I've inserted so far and tack it on to the very end, right? So insertion here would be an example. Insertion in a binary tree is another example of an algorithm where it's O of n, worst case time complexity, right? Because there's n things, and each time in the worst case, I have to compare against all of those things. And what's nice here about this O of n is that I know that on each of these steps, I'm doing more stuff, right? Like there's a comparison happening, and then I need to like find what the child is. But each of those things takes one step, right? And I don't care so much about that. What I really care about is the fact that it's taking linear time on the order of n to go through the whole thing, right? That's what really dominates this. Cool. There's going to be an assignment problem that asks you to fix this binary tree so that the worst case insertion becomes O log of n. Oh yeah, actually, this is a great example of something we actually will see insertion times that are smaller than n. So I can go back to what I wrote a second ago. Lecture 13. Find max. I called it find max, but we did a lot more stuff. So another really, really common one that you'll see for like searching and insertion and stuff is like log of n, just log of n. And there's going to be an assignment problem that asks you to fix the binary tree so that the insertions in the worst case only take log of n instead of n. Yeah. Okay. Any more questions about this? If you don't feel like you know too much what's going on right now, that's totally okay. This is one of those topics where it takes a little bit of time for things to really sink in. So don't feel too frightened. There'll be many, many opportunities to practice this on the upcoming assignment. Yeah. No, I'll like break it down in the, yeah, don't worry. I'm not just going to be like I wouldn't just throw this at you and be like, figure it out. We're gonna, yeah. Um, okay, cool. So, and in fact, there's another asymptotic complexity class that you see a lot, and it's just called O of 1. And this is about as fast as it gets, O of 1. Another way of saying this is constant time. In other words, the operation, whatever function you're writing, does not depend on the size of the input at all. Can anyone think of an example of a constant time operation that we've seen last class, maybe, last lecture? Okay, let's go take a look at it. So, yeah. Yeah, yeah. So that's a good example of like just assigning a Boolean is an example.
Either in or
Ah, good. Okay, good question. So what's actually happening under the hood in to find out whether or not something is in a list, it technically needs to traverse the whole list. So this is another really good example of one of those lines that isn't just one step. It actually takes like on the order of n steps to evaluate that. Okay, let's take a look. So go to lecture 12, hash table. What did I call it? So remember our good friend, the hash table. So inserting into a hash table is an example of uh, a function that only takes O of 1 time, right? Assuming it's like making a couple assumptions on how we've set up the hash table. But this insertion, you'll notice it does not depend at all on um, the size of the list, right? The number of buckets that we have. This modulo operation always runs an O of 1 time, and then assigning always takes 1 time step as well. So regardless of how many things are in the hash table so far, this insertion operation, as we've written it right now, without worrying about like chaining or probing or any ways of fixing collisions, takes O of 1 time, asymptotic time. It doesn't depend on it at all. Okay. Okay, so in the last 10 minutes of class, I'm kind of bummed. All right, I'll save it for next time. I had this really cool demonstration with cards I wanted to show you guys, but it'll give you something to look forward to next class. Uh, okay, so this was one way of doing this, right? Find max partial sum. And we'll call it like 1 to indicate that it's a first attempt at it. But in the very beginning of class, there was a much smarter suggestion, or not in the beginning of class, like when I first asked you how to do this problem, there was a way smarter suggestion on how we could approach this, right? Whereas in the find max partial sum that we've written here, where does the kind of inefficiency come from? Like when we're, okay, so here it's 3, here it's 7, here it's 13, right? And then 20, 29. Like, this isn't really efficient because we're repeating a lot of work that we've already done, right? In particular, when I want to know what the partial sum up to this point is, I have to recompute the sum from the start of the list up until this point. When in actuality, the way that we're doing it in our heads probably is we're just looking at the previous partial sum that we computed and adding what the current element is to that, right? So a much smarter way of doing this is, well, don't reinvent the wheel every single time. Just look at the previous sum that you had and add the current element to that, right? So let's rewrite this now in this smarter way. Okay, so now we're gonna do definition, find max partial sum 2. And the way we're going to do this is we're going to say, okay, again, we're going to have the temporary max stored as the first thing at the beginning. And now here's how we're going to do it. We're going to say, okay, we're going to iterate through this for I in some list. What we'll do is we'll keep track of the running sum so far. Running sum, which is just equal to temp max at the beginning, right? The first thing in the list. Sum list. Do I want to do it this way? Yeah, that's fine. Okay, and now what we're going to do is we're just going to say the new sum is equal to, how should I do this actually? The running sum plus I. And now we can compare if the new sum is equal to or is greater than the temporary max that we've seen so far. Temporary max is equal to new sum. And at the end, we'll just return what the temporary max is. But not before we update what the running sum is, right? And then we'll say, okay, now the running sum is equal to, honestly, we could even call this previous sum. Yeah, I think that's a better way of doing it. So on the first iteration, we'll say the previous sum is 0. Yeah, that's good. And then we'll say, okay, the previous sum, update it for the next iteration is equal to the new sum. So this is another way of solving the exact same problem that we did before, right? Does everyone agree that this works? Like we can kind of see, all I've done is code the intuition of what we were doing before, right? Like we look at the previous sum and we add I to what it was to get our new sum, and this is the thing that we're comparing to our temporary max, right? We're recording this and then returning this at the end. So different approach solves the same problem, but way faster, right? Like there's no repeated work that's happening. I have no inner loop here anymore. I've cut that out. So what's the asymptotic worst case runtime of this? What have we shaved this down to? Does anyone want to try? It's going to be big O of something. But big O of what? Is it still big O of n squared? Is it constant time? Is it big O of 1? No, because we still have to go through the list, right? So what is it? Yeah, exactly. This is big O of n, right? So worst case asymptotic complexity now is big O of n. So we've gone from O of n squared with this previous solution to O of n here, right? And so all of this is just to illustrate that when we talk about time complexity, we're not really talking about the problem that you give me, the problem that it solves. We're talking about your approach, the algorithm that solves that problems. And as you can see, there are good ways of solving problems and less good ways of solving problems, right? So this solution is a lot more preferable to the one before it. Yeah, any questions about this? No? Cool. I guess we have like, how are we doing on time? We have 5 minutes left. In the last 5 minutes of class, okay, what I'll do is, I kind of want to see if I could do like an optional demonstration of the difference between the runtimes, or like actually demonstrate.